Okay, so lesson 34 is a grouping of a lot of ideas together. The first one we're going to talk about is the mean value theorem for integrals. Now, we have a mean value theorem for derivatives, so now let's look at it as integrals. So first of all, there's a couple of things. The function has to be continuous. So if the function is continuous and this value c is in between the interval a, b, then there is some point on that graph, the c value. Every graph in that will have an integral from a to b of f of x, which remember is just the area under the curve, will equal at some point c the area of the rectangle created by this c. So let me show you a graph to help you see if we can see this visually. Okay, so first of all, let's look at what this first part of the function is saying. It's saying that the integral from a to b of f of x. So the integral from a to b of f of x is this entire area under the curve, right? Including this piece here. It goes all the way up to the curve, this piece here. It's the area under the curve, okay? So it says at some point c. So at this c value, now if you look at what this is giving us, it's giving us an area of a rectangle. F of c is the height, so this point here is f of c. So this tells us the height of the rectangle. The b minus a tells us the width of the rectangle. So they're saying at some point on the graph, if you create a rectangle with the height of that value at c, there will always be a point where this rectangle's area is equal to the area under the curve from a to b. Okay, so this rectangle is the second part of this function. Is this whole thing just the rectangle. So think of this as just a rectangle. Sorry, that's a lot of scribbling over the top of each other. But what you'll notice is if I draw another one right here, let's get another little example, is there's a point where the area will have the same difference being excluded on this side, or I should say included with the rectangle, excluded from what's actually the area under, but then this area will make up for it. So depending on where c shifts, you can create the exact area between that. Now that is the average value of the integral too, so we're going to look at that in just a second as well. Okay, so all they're saying is that any graph that is continuous and has a point c in between a and b, it is possible to find a point that will always make this equation true. That the area under the curve from a to b will be equal to the rectangle created from point f of c. Okay, so really what the mean value theorem makes it possible for us to do is to find the average value of a function on an interval from a to b. So this is the average. So if you look at the average value theorem, you'll see how it is just the integral theorem, the mean value integral theorem, rearranged. So the average value theorem tells us that f of c, which is our average value that's in our function here, is equal to 1 over b minus a times the integral from a to b of f of x dx. So this is really what makes it possible to find that average theorem, is the fact that this is true for every equation that is continuous and has that point between a and b. So if you think of it this way, so then this is, so remember this was the height of the rectangle and this is the width of the rectangle. So then all you'd have to do is divide by this function, this number value over here, and that's what this is, to solve for f of c. So finding that average value is usually what you'll be asked on the calculus test, is to say, find the average value of f of x on the interval from a to b. So let's try an example of using that average value theorem. Okay, so if we're asked to find the average value of f of x equals x squared in the interval from x equals 2 to x equals 4, we can use that average value theorem. So we're going to say, okay, we're trying to find f of c. So f of c equals 1 over b minus a. So this is our interval that we're looking at, so it would be b is the 4, 2. So we want to find how how wide is that interval there? And then we want to know from 2 to 4 of the function x squared. Okay, so let's go through and calculate this really quickly. So this would equal, this is just 1/2, and then we're going to take the integral, of x squared, which is x cubed over 3. And I'm going to integrate that from 2 to 4. So then I would get 1/2. Okay, so now I'm just keeping this 1/2 here, and now I need to do the evaluation of this, right? So I'm going to calculate with 4 plugged in first. So 4 cubed is 64 over 3. Then I'm going to subtract from that 4 plugged in. So now we have, or 2 plugged in, sorry. So 2 cubed is 8 over 3. So then we multiply that all out and we would get 28/3. So what does this tell us about the function? So let's look at what this is saying. So we have the graph x squared. Okay, and sorry, I wanted to redraw my graph here a little bit more accurately to kind of show somewhat accurately. So x squared of 1 is 1. X squared is 0 is 0, and then when you go to 2, it jumps to 4, 3 up to 9, and then by 4, you're all the way up to 12. So your graph is like this, more very steep curve. And the same thing on the other side. So they want us to look from 2 to 4. Okay, so we're looking at from 2 to 4. And they want to know what is the average value. So right now, this area all underneath the curve, they want to know what, so with the mean value theorem, we're saying that there is a point C that creates the same area underneath the curve using just a rectangle. And that point C is at f of C, the f of C is equal to 28/3. So 28/3 is 9.3, right? So right about here, somewhere just above here, is where that is what the average value, where the average value is. So if you were to create this rectangle, the area of this rectangle would be the same as the area just under the curve of the entire thing. And this is kind of what I was saying before. If you notice, it's like it adds on this little section of the graph that's left out in this section. It'll always even out that way. That's what the average value theorem is set up to find, is that. So then the answer would then be 28/3. So let's look at it now again. So that's where the average value is. That's the average value of where you find where it equals each other using that mean value theorem for integrals. Okay, we'll do one more quick example. If you're asked to find the average value of f of x of sine of x on the interval from 0 to pi, then we would do the same thing. You're looking for 1 over b minus a, which is just your interval that you're looking at. So this is the width of the interval, dividing by the width of the interval. And then we have the derivative, or the integral of, from a to b, of sine of x and dx. And then we're going to just, so this is supposed to be, sorry, if I was actually putting my values in here, this would be from 0 to pi of, and I left my x out too. Okay, so now we have 1 over pi, and the integral of sine of x is the negative cosine of x. And we're going to integrate that from 0 to pi. So let me get 1 over pi. Okay, that's an equals. 1 over pi of negative cosine of pi plus cosine of 0, which that would give us then 2, because the cosine at 0 is 1, and so is the cosine of the negative cosine of pi is also 1. Sorry, it's 1. So anyway, so you would have 2 is the evaluation of that. And then you'll just have this equals 2 over pi. Okay, so that's pretty much what you need to know about the mean value theorem, is that they're going to ask you to find the average value, and you need the mean value theorem to find the average value of a function. Okay, the next concept that we're going to go over is the second fundamental theorem of calculus. So the first fundamental theorem was being able to evaluate an interval across an integral through an interval. So the whole f of b minus f of a, you can look back into the last one if you have questions about what the first fundamental theorem is. So that's the first, one of the most important things of it, right? So the second fundamental theorem is the idea that if you have a continuous function, that you can, then the derivative of a function undoes the integral. So basically, the derivative and the integral are inverses of each other, right? So in math language, if f of x is continuous, which it is important, it does have to be continuous to be able to be differentiable as well. So if it's continuous on the interval from a to b, then the derivative, so think we're taking the derivative again, of the function f of x, so the derivative of the integral, then that will give us the derivative of our integral, so it's the derivative of f with respect to x, which is the same thing, it's equal to the derivative of the integral, and that will give us just f of x. So before we go into more detail about what this is, let's just talk about really quickly the same type idea. If I have the value 6, and I multiply it by 2, I get 12. And then if I take 12 and I divide it by 2, I get 6 again. So if you go back and forth, you get back to your original function. Now this is the only thing about this, is that when you take an integral of something, you lose, or when you take the derivative of something, you lose that constant, right? So this value of a, whatever you're integrating from a value up to your variable x, it doesn't matter at all what the value of a is, because when you take the integral, that constant is going to be gone again. So let me see, I'll see if I can explain it better. But on here, so basically, you know you're going to be using the second fundamental theorem of calculus when you see a variable in your integral and you're asked to take a derivative of an integral. Okay, so the questions on the AP test are actually pretty straightforward as far as using this, this idea. So let's look at an example really quickly. So if I want to know, like this is the type of thing that you would see it in, it would say find, and you're going to really be conscious of when you see a derivative and an integral next to each other. Okay, so if I want to know what the derivative of the cosine of t is, that this is as straightforward as saying if you're taking the derivative of the integral from 1 to x of cosine of t, according to the fundamental theorem of calculus, the second fundamental theorem, this is just the cosine of x. Okay, so it's pretty straightforward in a simple problem like this. So let me explain better why this value down here is considered a dummy value. It doesn't actually matter what it is. So let's look at each of these. If we're looking for the derivative of the integral from 0 to x of t equals dt, or d dt, t dt. So the way the second fundamental theorem calculus tells us is that this value is just equal to x. Well, this one is going from 2 to x, and we also would say that using that theorem that this just equals x as well. So let's look at it. Let's actually do the problem and see. Let's do the problem the long way without the theorem. So we're going to take, first of all, I'm going to take the integral of t with respect to t and evaluate it from 2 to x. Okay, so we're going to still have our d dx out here, and we're going to work on the inside part first. So we would get t squared over 2, and we're going to evaluate that from 2 to x. Okay, so then we're still going to take the derivative. We're leaving that there while we calculate this inside. So we plug in x in, we get x squared over 2 minus a 2 plugged in, which would give us 2 squared, 4 divided by 2. So this would just be minus 2. So now that we have that evaluated, we would now take the derivative of the function that we integrated. So when we take the derivative, you bring the 2 down, you get 2x divided by 2 minus 0. So you see how that just equals x. Well, it doesn't matter in this one that you're going from a different interval, that dummy value there, because the same thing happens. We'll just really quickly. If we're going to take the derivative of the integral is still just the t squared over 2, and we're evaluating now from 0 to x. What happens is that now we'll say, okay, well, we have x squared over 2 minus 0. But do you see how when you take the derivative of a constant, it will always be 0. The derivative of a constant is 0. So this value creates a constant that when you take the derivative, it goes to 0. So it doesn't actually matter. So don't let this value mess you up at all. You can use the theorem just to say that that is equal to just x. So let's do one that has, let's say, if it go from, we want to know the derivative with respect to x of the integral from 2 to x of 1 minus t cubed dt. Sorry, my pen is not working very good today. So we can do the long way and take the integral and evaluate it and then take the derivative, or using the theorem, we can say, oh, well, this is just going from 2 to x, and we're taking the derivative and the integral. So all that's going to happen is we're going to get 1 minus x cubed. So it'll be the function here with the x replaced in place of it. So one thing I want to mention right now, too, is that if you have this value c in between a and b, then you can split your integral up and take areas under the curve in different sections at different times. So for instance, if I want to go from a to c and take the integral of that, that would be the area under the graph from a to c. And I can add to that the area from c to b, and that'll still give me the same area as the whole thing. So if you think of it like as a graph here, and this is A, C, and B, then you could take this area first and then this area, and you can add it together, and it's the same as taking the whole area. Okay? Which actually, the way that I drew it, we're going to need to use that. I'm going to talk about that more in a second. Or soon. The last thing that I want to talk about with the second fundamental theorem of calculus is what about if this value is not x? So for instance, how it's x squared as opposed to just having a plain x there. We have to use the chain rule. So on here, you're going to have, before we just plugged the value x into there, right? So it would be 1 minus, and usually it would just be x cubed, but we have x squared is our term. So now we do have to not only, we have to multiply by the derivative of the inside function also. So this then, we'd have to multiply by the derivative of x squared, which is 2x. So then our whole answer, we would multiply this out, so we would actually get 1 minus, because the powers are outside of the parentheses, you multiply them together, and then we would still be multiplying by that 2x. So you need to multiply by the derivative of that inside function to do these correctly if you don't have just a plain x there. So let's do one more example. Let's take the derivative of from 0 to 3x to the 4th of t plus 4t squared. So a lot of times, yeah, for me, when you guys are doing these problems, I just have to start associating things and be like, oh, okay, this is how I know if I need to use this, is when I see, anytime I see the derivative and the integral together. Another indicator is when they have other variables in there. They usually will have like the x's and the t's together. Okay, so now let's try and solve. Let's solve this problem together. So we're going to, t will now be 3x to the 4th. But we have to use our chain rule, and we need to multiply this by the derivative of the inside function. Okay, and then you would simplify your problem down. So I want to just touch really quickly on the idea of accumulation function. So an accumulation function is when this interval is changing. So the x, as x gets larger, you're integrating a different value, right? So this is the same thing where you're going to have these values of t in here, and you can integrate this. So we can take the integral of t, which is t squared over 2, and we can evaluate it from 0 to x. So then we would get x squared over over 2 minus 0. Okay, so in this case it would be 0. But all that they're looking for, so we don't even know what the x value is, but we do know that this graph is just the line that looks like this, but actually goes through 0, 0. But if you're looking at as x increases, so for instance, let's say when x is at 2, this is the area under the curve from 0 to 2. Well, if you then evaluate it at 4, it's the area from 0 to 2 as well as the area from 0 to 4. So it's accumulating more area as it goes. Okay, the last thing I want to talk about in today's lecture is the idea of finding an area of an integral without using integration. So, for instance, if you are given a picture and not an equation. So let's say that I have this graph here, and it is this line. They don't tell me what the line is, but they do tell me that I want to find it from 0 to 3. And that this point is the point 3, 2. Okay, well, we have enough information here without having to know. Like, we could find the equation of the line, but we can find the area under the curve just by using algebra, and in this case trig to some extent, just finding the area of a triangle. So the area of a triangle is 1/2 base times height. So if I do 1/2, the base is 3, and the height is 2. Then this would be the area of 3. Okay, so let's look at like another super simple one. Let's say that this is just the line y equals x. So this is example 1. And I'm going to keep them really simple so that I can just show you the basics of what we're talking about here without, like, if I'm making them up in my head, I don't make up something that's too ugly for me to work on right here. So what I wanted to show you, though, is, like, let's say that this is 3, and they just tell you that this is the point 3, 3, right, because y equals x. So we could use it finding area. So the area under there of the triangle is 1/2 base times height, which is going to be 9/2. Or you could find the same thing taking the integral of x from 0 to 3. Just wanted to show you how this is the same thing. So then here we would get x squared over 2 from 0 to 3 is equal to 3 squared, which is 9, over 2 minus 0, which is 9/2. So you can find, and so I want you to connect two things, two ideas. One is really understanding in your head that the integral, visually, the integral is the area under a curve. The second thing is that finding this area by hand is the same thing as finding the integral. Something else that you'll see is possibly that they want you to find the area of this from 2 to 3, and they want to know this. Well, you can also find the area of the whole thing, which we did, the 9/2, and then subtract from it just the area of that front little triangle, and that would also give you the area that is encased here just using shapes on your graph.